Hello everyone, this is Poorani. We saw the 5 sums in page 150 of chapter 9 class 10 NCERT textbook in the previous video. We will see the lesson further in this video. As we see, this is the refraction by spherical lenses. So the next part we are going into is spherical lenses. We saw so far about mirrors. Now we are going into spherical lenses. We saw rectangular glass slab. Now this is refraction by lenses. So as we see, there are two kinds of lenses, convex lens and concave lens. We previously saw about mirrors. We saw about concave mirrors and convex lenses. Now this is about concave mirror and convex mirror. Now we will see about convex lenses and concave lenses. So as you see, this first diagram represents the convex lens. As you see, this convex lens is thicker in the middle. The middle area of the convex lens is thicker and the edges are thinner. So this represents a convex lens. It has two spherical surfaces. Now this second figure here shows a concave lens. Concave lens has a thicker outer edge and a thinner middle. The middle of the lens is thinner. So as you see in the ray diagram, this convex lens is a converging lens and concave lens is a diverging lens. So then as you see, there are two spherical surfaces for the lenses. Each of this spherical surface forms part of a sphere. When we saw mirrors, we saw the mirror forms a part of a single sphere. Yes, now we have two spheres. As you see, this surface will form a sphere. When we see it here, there is this, the lens is here. Yes, when you complete this part, you will have a sphere and this surface will form a part of a sphere. So we have two principal axes now. Yes, so the line joining these two principal axes C1 and C2 will give you the principal axis. Now the central point of the lens here, say this point here, will give you the optical center. Similarly for a concave lens, yes, this center point of the lens will give you the optical center. Now the diameter of the circular outline of the lens is called the aperture. What do we mean by this is, there is this outline, right? The lens has a outline. This outline, yes, I'm sorry for this thing, yeah, this outline and this diameter, yes, will give you the aperture. I'll try to do it much clearer. The lens is here, right? And the diameter, this diameter will give you the aperture of the lens. Yes, now we are going to see about thin lenses in this chapter. So what do we mean by thin lenses? It is related to this aperture. When the aperture is much lesser, the aperture of the lens is lesser than the radius of curvature, we call it thin lenses. So when we talk about thin lenses, we are going to see that the aperture, which we just saw, aperture is lesser than, very less than the radius of curvature. We already saw what radius of curvature of the lens is. So when the aperture is very less than the radius of curvature, it is called a thin lens. So now we see in the diagram that the rays of light falling parallel on a convex lens converges at this point, which is called the focal point or the principal focus, F. Yes, this we call it as the optical center O. So then we have the center of curvature of both the sides, say C1 and C2 somewhere here. So this is for the spherical, this spherical side and the other spherical side. We have C1 and C2. So similarly we will have this to be F2, and when you pass light from this side, say when we pass light from this side, we will have image formed on the other side, say here. So this we will call it as F1. So we will have two center of curvatures for both the spherical surfaces and two focal principal focus F1 and F2 for both the spherical surfaces. Yes. So as we see, this convex lens is a converging lens and it converges the ray of light, parallel ray of light at the point at the principal focus. Similarly, for a concave lens, it is a diverging lens, and when parallel rays of light falls on the lens, it appears to diverge from this point. Say this is the principal focus F1. Similarly, we will have a principal focus F2 on the other side of the lens. Yes. So now, as we saw earlier for the mirror, small f denotes the focal length. What do we mean by focal length? It is the distance between the optical center, this optical center O, and the principal focus. So focal length f, this is f. So we will go to the next part, which is the image formation by lenses. So we saw image formation by mirrors in the previous videos. Now this is image formation by lens. Similar to the mirrors, we have 6 positions of the object. When we place object at these 6 positions, we will get the image corresponding to the position of the object. Yes, the first one here is the object is placed at infinity. This is what we saw in the previous ray diagram. Yes, when we have parallel rays of light, the image is formed at F2, which is on the other side of the lens. Yes, when the object is placed at infinity, the parallel rays falling on the lens will form image on the other side of the lens at F2. Yes, it is a highly diminished image or point sized image. This image is real and inverted. So again, when we place the object at beyond the point 2f1 on the to the left side of the lens, we get the image between f2 and 2f2, so which is diminished, real and inverted, and the nature of the image is real and inverted. When you place the object as at 2f1, you get the image at 2f2. It is the same size as the object, real and inverted. So when you place between f1 and 2f1, the image is formed beyond 2f2. So when you place the object at f2, you get the image at infinity, which is highly enlarged. Yes. So now for the last position, we have between f1 and the optical center O. So this we are seeing it as a tabular column. Similarly, we will see a tabular column for concave lens also. We have only 2 positions for concave lens. One the object is placed at infinity, and the next position is between infinity and the optical center O. So what we get is, we get a highly diminished point sized image which is virtual and erect, and both the cases we see that the image size is diminished and it gives a virtual and erect image. From this we can say that the concave lens will always give us a virtual, erect and a diminished image. So now, after this we will see how this image is formed using ray diagram. So the next thing we will see is image formation of lenses using ray diagram. For the mirror also we saw ray diagram, and we will use the same principles. There are 3 points which we have to remember when we are drawing ray diagram. The first thing is, a ray of light from object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens. So this is what we have in the first. So this ray of light which is parallel to the principal focus is passing through F2, which is on the other side of the lens. Similarly, in case of a concave lens, what we have is this ray of light which is parallel to the principal focus here, principal axis here, appears to diverge from the principal focus on the same side. Yes, it appears to diverge from F1. This is point number 1. The next point is, a ray of light passing through the principal focus after refraction will be parallel to the principal axis. Yes, so this ray of light which is passing through F1 on the left side of the lens, getting after refraction at the lens, will travel parallel to the principal axis. Yes, on the other side of the lens it will be parallel to the principal axis. This is for the convex lens. So for concave lens, a ray of light appearing to meet at the principal focus of the concave lens after refraction will emerge parallel to the principal axis. So this is what we have. So this ray of light which appears to meet at F2 is parallel to the principal axis after refraction. So this is the second point. Now for the third point, what do we have? A ray of light passing through the optical center of the lens will emerge without any deviation after refraction. So this ray of light which passes through O, the optical center of the lens, will pass without any deviation for both the cases, for both convex and concave lens. So these 3 points we have to remember when we draw a ray diagram. So we take 2 rays to form a image. When we draw 2 rays and we make it meet, so we will get the image at that point. This is very similar to the mirror which we did in the previous videos. So these are the positions. These 6 positions is what we have seen in the tabular column. Yes, so we will go through this with the ray diagram now. For each position we have ray diagram. So this, as you see, this first figure here is for the object which is placed at infinity. So we have parallel rays of light falling on the convex lens. After refraction, they all meet at this point F2 on the right side of the lens. Yes, so here we get a diminished point sized image. This is again a real and inverted image. Yes, this is the next position. What do we have beyond 2F1? F1 is here. F1 is the principal focus. What do we see here is 2F1, which is the center of curvature C. Yes, C1 here, which is on the left side of the lens. So when you place an object beyond this point C1, what we have is the image which is formed is between F2 and 2F2, which is between F2 and C2. Yes. So now the next position is at 2F. This picture, this figure here will show you the object is placed at 2F here. This, when you place the object here and draw two lines, two rays, one which is passing through the optical center and one which is parallel to the principal axis. When they meet after refraction, we find that the image is also formed at 2F2. Image placed at 2F1, object placed at 2F1 will form a image at 2F2. Yes, so this image is at the same size as the object and real and inverted. Yes, now the fourth position, which is between F1 and 2F1. So this between C1 and F1. At this point, when you place the object and draw two rays, one which is parallel to the principal axis and one passing through the optical center, and make it meet, what do we find is, we find that the image is formed beyond C2 or 2F2. Yes, so this is an enlarged image, enlarged and real inverted image. Yes, so the next position is at F1. So this, when you place the object at F1, we find that the image is formed at infinity. So when this image which is formed at infinity is highly enlarged and real and inverted. Yes. So the next, the sixth position is the position of the object is here, which is between F and O. Yes, between F and the optical center. This is F1, which is on the left side. Between F1 and O, you place the image and draw two rays, one which is again parallel to the principal axis and one passing through the optical center. What do we see is these two lines do not meet on the right side. So what we do is we extend it backward and see where it meets. So we find that the image is formed on the same side as that of the object. It is not on the opposite side, it is not on the other side of the lens, it is on the same side of the lens as the object, and this image is enlarged, virtual and erect. Yes, so this one image we get as virtual and erect image for convex lens. So these two pictures will show the image formation of a concave lens. Yes, first one, the object is placed at infinity. So when you place it at infinity, we draw two parallel rays parallel to the principal axis, and it appears to diverge from this point F1. Yes, so the image is highly diminished point size image, virtually erect image. It is formed on the same side as the object, not on the other side of the lens. Yes, so it is a virtual and erect image. So the next position for the object for a concave lens is anywhere between infinity and the optical center O. So the object is placed here, say, when the object is placed here, so this A, B is the object, and you draw two rays, one parallel to the principal axis and one passing through the optical center, and it appears to meet at this point. Say this is where the image is formed. So this again is a diminished image, virtual and erect image. So this is the image formation of the lenses using ray diagram. So the next thing we will see is the sign convention. So sign conventions for spherical lenses is the same as sign convention for spherical mirrors. So we will go through the same points which we saw for mirrors. The first thing is the object is always placed to the left of the lens. This implies that the light from the object falls on the lens from the left hand side. So that's what we saw in all the ray diagrams. Yes, all distances parallel to the principal axis are measured from the optical center of the lens. Yes, all the distances measured to the right of the optical center, right of the origin is taken as positive, while those measured to the left of the origin is taken as negative x. Yes. So the next thing is distance measured perpendicular to and above the principal axis is taken as positive, and the distance measured perpendicular to and below the principal axis taken as negative. So these 5 points which we saw for mirrors, spherical mirrors, holds good for spherical lenses also. Yes. So the next thing we will see is the lens formula and magnification. For lens formula, what do we have? 1 by V minus 1 by U is equal to 1 by F. It is very similar to the previous lens formula we saw. Yes, where V is the image distance, U is the object distance, and F is the focal length. Yes, we will write it down here. So in this formula, what do we have is V is image distance, the distance of the image from the optical center. U is the object distance from the optical center, and F is the focal length of the lens. Yes. So this formula we can use to find the focal length when the other two values are there. From when we have image distance and object distance, we can find F, and we can find any of it when the other two values are given. Yes. Now the next thing is magnification, where M is the magnification, which is height of the image by height of the object, H dash by H. This we already saw is also equal to V by U, where V is the image distance and U is the object distance. Yes. So the next thing we will see is power of a lens. What do we mean by power of a lens? It is the degree of convergence, or divergence of a lens. Yes, this is the degree. P or power is the degree of convergence or divergence of the lens, and its formula is P is equal to 1 by F, and its unit is diopter. Diopter, which is denoted by the letter capital D. Yes, when you have the focal length in the SI unit, which is in meters, when F is given in meters, we can find the power of the lens from the formula 1 by F, which will be given in diopter. Yes, we see that the convex lens will have a positive power and concave lenses will have negative power. Yes. With this we finish the lesson. Yes. We will see the example sums and exercise sums in the next video. For doubts and clarifications, contact the WhatsApp number given in the description box. If there are any sums you would like to get solved, if you want me to solve any of the problems you have, you can always send it to me to the WhatsApp number given in the description box, and I will solve the problems and send it to you. Yes. Thanks for watching. Happy learning.